In calculus, we often talk about finding the area under a curve. This might sound a bit abstract, but it has many applications in the real world. Imagine a graph showing the speed of a car over time. The area under that curve represents the distance the car traveled. This is where integrals come in. An integral is a mathematical tool that allows us to calculate this area. Integrals are fundamental to calculus, just like their counterpart, derivatives. While derivatives tell us how a function changes at a particular point, the slope of a curve, integrals give us the cumulative effect of that change over an interval. They are like two sides of the same coin, each providing crucial information about a function's behavior. Let's visualize this with a simple example. Consider a straight line graphed on a coordinate plane. The area under this line forms a geometric shape, like a triangle or a rectangle, depending on the line's slope. We can easily calculate this area using basic geometry. However, when the curve is not a straight line but a more complex shape, things get trickier. We can't use simple geometric formulas anymore. This is where the concept of integration becomes powerful. The concept of the area under a curve might seem abstract, but it has many real-world applications. For example, consider a car accelerating at a constant rate. We can represent this acceleration with a graph where the x-axis is time and the y-axis is speed. The area under this curve, which represents the distance traveled, is not a simple geometric shape. To calculate this area, we need to use integration. One way to approach this problem is to divide the area under the curve into smaller rectangles. We can then calculate the area of each rectangle and add them up to get an approximation of the total area. This method is called a Riemann sum. The more rectangles we use, the more accurate our approximation becomes. In essence, we're trying to approximate the curve with a series of straight lines, making the area calculation simpler. Section 5. The power of the fundamental theorem of calculus. While Riemann sums give us a way to approximate the area, the fundamental theorem of calculus provides a more elegant and precise solution. This theorem establishes a direct link between derivatives and integrals, revealing them as inverse operations. It states that to find the definite integral of a function, we can find its antiderivative, which is the reverse operation of finding a derivative, evaluate it at the interval's endpoints, and subtract the results. This powerful theorem revolutionizes how we approach integral calculus, providing a direct method for precise area calculation without resorting to approximations. Section 6. Beyond simple shapes, integrating complex curves. The beauty of integrals lies in their ability to handle even the most complex curves. Whether it's a trigonometric function like sine or cosine, an exponential function, or a combination of various functions, integrals provide a way to measure the area they enclose. This ability to handle complexity makes integrals an indispensable tool in various scientific and engineering disciplines. Section 7. Different techniques for different integrals. Just as there are different techniques for solving different types of equations, calculus offers a range of techniques for evaluating integrals. Some integrals can be solved directly using the fundamental theorem of calculus, while others might require more advanced techniques like integration by parts or substitution. These techniques are like tools in a calculus toolbox, each suitable for specific types of integrals. Mastering these techniques is key to tackling the diverse world of integral calculus. Section 8. Integrals and action applications across fields. The applications of integrals extend far beyond the realm of pure mathematics. In physics, integrals are used to calculate work, center of mass, and the motion of objects. In statistics, they are essential for understanding probability distributions. In engineering, integrals are crucial for designing structures, analyzing fluid flow, and optimizing systems. The ability to calculate areas and volumes with precision makes integrals an indispensable tool in countless real-world applications. Section 9. Conclusion. The enduring significance of integrals. Integrals, along with derivatives, form the bedrock of calculus. They provide a powerful way to analyze the behavior of functions and solve a wide range of problems involving accumulation, change, and measurement. As we've seen, integrals are not just abstract mathematical concepts, but tools with far-reaching implications. They help us understand the world around us, from the motion of planets to the behavior of subatomic particles.